Welcome back to the aerodynamics class. Today our discussion is on circulation, steam function and potential function. I acknowledge John D. Anderson's Fundamentals of Aerodynamics. Right. Now, what is circulation? As I was discussing, circulation is a fundamental tool which we use to calculate the aerodynamic lift in all our discussion in the near future, right? So this was used independently by Frederick Lancaster in England and Wilhelm Kutta and Nikolai Zhukovsky. So in the next few classes we will discuss the famous Kutta-Zhukovsky relation, which is very famous in aerodynamics, right? So we will have a detailed discussion on all those things, right? So these names, Frederick Lancaster, Wilhelm Kutta, and Nikolai Zhukovsky, they are from the different country, England, Germany, and Russia, respectively, and they have used this particular term circulation and have contributed a lot in the area of aerodynamics. Now, let us start with the circulation and say you already know this particular curve, closed curve C, and you have the ds be the directed line segment, right? And for this case, we want to define the circulation, which is mentioned in terms of gamma, right? Gamma is the term we use for circulation, right? So the gamma is a circulation which is defined by the negative of the line integral of velocity around the closed, right? So here you have a curve C, and the definition we say for gamma is equal to minus line integral of velocity around a closed curve, right? So please note this definition of the circulation. And circulation is a kinematic property, right? So it is depending only on the velocity field and the choice of the curve. So V is the velocity and ds is the line segment, right? So please note this information. Velocity and ds is the line segment. So this word circulation has lot of discussion. If you read John D. Anderson, you will come to know in the American Heritage Dictionary, the circulation is simply defined as movement in a circle or a circuit, right? But in aerodynamics, circulation has very precise technical meaning, right? So we cannot simply take that circulation mentioned, right, in the dictionary. So circulation also related to the vorticity, right? That we will discuss, right? So if we consider an airfoil and there is a flow over the airfoil, the circulation is one way or other, it contributes to the lift. So you should not think that the circulation is something which is circulating, right? It is not something which is circulating, but the contribution of the component that in turn related to the lift force produced, that we will discuss in detail later. So just for understanding, I am giving this airfoil example, right? Now I told we can relate the circulation to the vorticity, right? So here we can do that. So let us assume a surface in the flow field, right? We know that the surface, the elemental surface ds and the whole surface s, right? And the velocity at point P, right? This is point P, and we want to calculate the velocity at point P, right? Velocity at point P is v. We can define the velocity, right? So P can be at any point, and based on our Stokes theorem, we can write gamma is equal to minus of line integral of v into ds. So we can write the based on the Stokes theorem minus of double integral over surface s del cross v dot ds. V is a velocity field, right? And we can define v as ui plus vj plus wk. And you can see the d gamma is a circulation, and we will say finally d gamma is equal to minus del cross v dot ds, right? D gamma can be written as minus del cross v into ds, and here we can write in the unit vector, right? So ds can be defined, and finally we can write the d gamma by ds, which is del cross v dot n. So where here we know that ds is the infinitesimal area, right, with a closed curve C, that we have already shown in the previous slide figure. This is a closed curve C, and S is the surface, right? So d gamma by ds is equal to del cross v dot n. Now you can discuss about del cross n, right? You know the del cross n. What is del cross n? Del cross v, sorry, del cross v.
Vorticity, sir.
Yeah. What happens if del cross v is equal to 0?
That means the flow is irrotational.
Yeah. So if the del cross v is equal to 0, then the flow is irrotational, right? Okay. I stop at this point for the circulation, and we will continue our discussion for the stream function. What is the difference between vorticity and circulation? Vorticity, this is vorticity, right? This term, and we define this as the circulation per unit area. This is the S is the area, right? Okay.
Vorticity is vector, while we have circulation to be a scalar.
Yeah. Yes. So the component of vorticity normal to ds, and we can equate this to d gamma by ds. This is circulation per unit area. This is mentioned as circulation per unit area. So we will move to the next point, right? And the circulation is normally written as vorticity is defined as zeta. Now let us start the discussion of the stream function. You already know what is streamline, and you have some information about the steam tube also, right? So now I take, like in the last discussion, I was saying something called steam tube. It is almost like our hose pipe in the garden, right? And it is surrounded by a tube which can be said as analogous to the steam tube. So now we will have a discussion here as a two-dimensional flow, right? So here, let us consider this is a two-dimensional flow and it is a steady flow. We don't worry about the dt term. Okay. So let us consider a two-dimensional flow and a steady flow. Now, AB is a streamline which is mentioned by a stream function psi is equal to C1, and CD is the another streamline, right, which is mentioned as psi is equal to C2. And the distance between the two streamline is del n, right? So now we will discuss about the stream function. So let us say in this case the differential equation for the streamline that we have already discussed. What is the differential equation for this streamline? dy by dx is equal to v by u. So this is the equation for two-dimensional steady flow and two-dimensional steady flow and the equation for the streamline. Right? Do you remember? We have done x, y, and there is a streamline, and we have taken dy and dx, and v is the velocity and the velocity component u, v. Right? Now, say u and v are the known function. Let us say u and v are the known function of x comma y, and it can be integrated to finally get the equation for this streamline. So we can write f of x comma y is equal to c. Here c is an arbitrary constant of integration. Constant of integration. Right. So here the different streamlines, and finally we want to write a function psi of x comma y is equal to c. Right. And as I said, in this diagram, AB and CD are given as psi is equal to C1 and another curve psi is equal to C2. And we can say that del psi, let us write here, del psi can be written as C2 minus C1, which is in turn equal to the mass flow between the streamlines. Right? Now, we have a discussion here. Let us assume that the streamlines are close, very much closer, right? So it means that the velocity v is constant across this del n, right? This is del n, and the velocity v is constant across del n. Right? Now, let us calculate the mass flow. Let us calculate the mass flow through the steam tube. right? Let us assume that mass flow through the steam tube per unit depth perpendicular to the 2D, right? Perpendicular to the 2D means that from the screen we can have a perpendicular line, right? So we know already that del psi is the mass flow across. So we can write rho v into del n, and I take it as a unit depth. So del n into 1, and hence we can write del psi by del n can be written as rho v. So let us consider a limiting case. Let us say limit del n tends to 0. We can write rho v is equal to dou psi by dou n, right? Here the same diagram we have drawn, A and B, C, D, and here you have the streamline psi, and we consider the del psi, right? So this line can be psi plus del psi, right? And this distance we have considered as del n, right? And you have a velocity component v, and I said if del n is so small, then the velocity is constant across this streamline, and here v is the velocity, and let us write the component u and v, and we can take this del x, and this is del y, right? So we consider the xy plane. So based on that, we will further proceed, right? So the mass flow, I recommend you to have this diagram in your notebook so that when we derive, it will be easy. So if one want to calculate the mass flow across this del n, it will be like the summation of the mass flow through del y and del x, here minus del x, right? So the summation of del y mass flow through del y and minus del x is the total mass flow through the del n, right? Okay. Now let us write the mass flow. A mass flow that is equal to del I is equal to rho v del n, that can be written as rho u. I told it is del y plus rho v del x, and this x is minus, and hence I write minus there. Now let us have a point that let the CD which approaches to AB, let the CD is a streamline and AB is a streamline. I say CD approaches to AB. This is the limiting case, right? Then we can write d psi is equal to rho u dy minus rho v dx, right? So we have psi is a function of psi of x comma y. We can apply a chain rule, right? We usually have a chain rule in calculus. And we can write d psi is equal to dou psi by dou x into dx plus dou psi by dou y into dy, right? Now we have two equations, right? This equation, this is equation 1 and equation 2. We can compare these two equations, right? By comparing these two equations, we can write dou psi by dou x, right? Dou psi by dou x is equal to minus rho into p. Similarly, dou psi by dou y, that can be equated to rho u. So let us write that. So this is xy, and if it is in x and y, then we can say that it is in Cartesian coordinate system. So rho u is equal to dou psi by dou y, and rho v is equal to minus dou psi by dou x. So these are the equations for the stream function in terms of Cartesian coordinate system. So similarly, I want you to work for the polar coordinate system, right? System. So if it is in polar coordinate system, you need to write rho Vr equal to 1 by r into dou psi by dou theta, and rho V theta is equal to minus dou psi by dou r, right? So in this case, the psi can be applied to both compressible and incompressible case, since we consider the rho, right? Right. So if it is not, then we can say rho is not valid. So we will simply write u is equal to dou psi by dou y. So if we consider only for the incompressible case and rho is equal to constant, then we may write u is equal to dou psi by dou x dou y, and v is equal to minus dou psi by dou x, and Vr is equal to 1 by r into dou psi by dou theta, and V theta is equal to minus dou psi by dou r. So this is for the incompressible case. Right? So we have almost done with the stream function. Now we will discuss about the potential function. Right? Right? So before going to the potential function, we will just look into the velocity, velocity potential, and we will write the function. So we already know that the irrotational flow, right? We already know that the irrotational flow. Irrotational flow is defined as the flow where the vorticity is 0 at every point, right? Right, the vorticity is 0 at every point, right? So let us consider a irrotational flow and write the equation for vorticity is equal to del cross V is equal to 0, right? Now consider the vector identity, right? So let us consider the vector identity, and phi is a scalar function. Then we can write del cross del phi is equal to 0. So that means that the curl of the gradient of a scalar function is identically 0. So please note this: the curl of the gradient of a scalar function is equal to 0. So by comparing these two equations, say 3 and 4, we can now write V is equal to del phi, right? What is del phi? It is gradient of phi, right? So what it states, V is equal to del phi. It states that for a irrotational flow, there exists a scalar function phi such that the velocity is given by a gradient, right? There exists a scalar function such that the velocity is given by the gradient phi, and we denote this phi the velocity potential. So velocity potential can be a function of, that is equal to phi is equal to phi of x comma y comma z. In the case of polar coordinate system, phi can be a function of phi of r comma theta comma z. Or if it is in a spherical coordinate, we can write it as phi is equal to r comma theta comma phi. Right? So we will have a discussion with the Cartesian coordinate system. Let us consider the Cartesian coordinate system. So we already know a velocity field V can be written as Ui plus Vj plus Wk, right? So V is equal to del phi, right? Our discussion is V is equal to del phi. Then we can write this as dou phi by dou x of I plus dou phi by dou y of j plus dou phi by dou z of k. So we can write U is equal to dou phi by dou x. V is equal to dou phi by dou y. W is equal to dou phi by dou z. Again, in the cylindrical coordinate system, we can write in the cylindrical coordinate system. We can write VR is equal to dou phi by dou r, and V theta is equal to 1 by r into dou phi by dou theta, and Vz is equal to dou phi by dou z. Similarly, in the spherical coordinate system, we can write Vr is equal to dou phi by dou r, and V theta is equal to 1 by r into dou phi by dou theta, and V phi is equal to 1 by r sin phi into dou phi by dou phi. Right? So the velocity potential is actually analogous to the stream function in the sense that the derivatives of phi yields the flow field derivatives, right? So there you have dou psi by dou y gives u, but here dou phi by dou x gives u, right? Right? So both the velocity potential and the stream function is analogous to the, both are analogous in such a way that both yields the flow field derivative. Now there is a difference between this stream function and the potential function, right? So we will discuss about that. Say, for example, we will write point number 1. The flow field obtained by differentiating phi, dou phi by dou x, in the same direction as the velocities, right? However, in the case of stream function, this is dou psi by dou y, that is normal to the velocity direction, right? The flow field velocities are obtained by differentiating phi in the same direction as the velocities, where in the stream function it is differentiated to the normal direction. Second point, this is u and this is also u. Second point, velocity potential is a differential for irrotational flow. Right? Second point, the velocity potential is differential for irrotational flow. In contrast, the stream function can be either used as rotational flow or irrotational flow. We will do a few exercises later, right? And again, third one, the velocity potential applies to three-dimensional flows, where the stream function applies only to the two-dimensional flows. Right? So with all, we can have a conclusion that irrotational flows, we can write irrotational flows described by velocity potential, right, is called potential flows. What is potential flows, or what is potential flows is a famous question in the aerodynamics, right? So we can describe that as rotational flows, which can be described by the velocity potential phi, can be the potential flows, right? So this is all about the um, velocity potential. So today we have seen 3 points. One is circulation gamma, velocity, stream function, and the potential function. So it is possible to find the relation between the stream function and the potential function that we will discuss now. Right? So relation between relationship between psi and phi, right? So let us start with, say, for irrotational flow, for irrotational flow, we can write V is equal to gradient of phi. Right? So we can write again the line of constant phi. What is phi? Is a potential, right? Velocity potential. The line of constant phi is an isoline of phi, constant potential, and hence we can call it as isoline of phi, right? And since the phi is a velocity potential, we can call that as a equipotential line. Right? So this is about the potential. Potential. Now, please note, in addition, a line drawn in the space such that del phi is tangent at every point. What is tangent at every point? Tangent at every point. We know something about tangent at every point. It is defined as gradient line. So here del phi is equal to V, then this line is a streamline. Right? Right? So now we will write the streamline is a line with the constant psi. Streamline is a line with the constant psi, right? Here, streamline is a line with the constant psi. Right? We already know that the gradient lines and isolines are perpendicular, and hence equipotential lines what is equipotential line? Where phi is equal to constant and streamlines. What is streamlines? Where psi is equal to constant or mutually perpendicular. Right? So, to study the relationship between the stream function and the velocity potential, we will start with the consideration. Let us consider a 2D flow, irrotational flow, and incompressible flow. In Cartesian coordinate system. We can write for streamline psi of x comma y is equal to constant, right? So we can write d psi that is equal to dou psi by dou x into dx plus dou psi by dou y into dy, and we already know the d psi by dou psi by dou x is equal to minus v dx plus u dy equal to 0. dy is equal to 0, and hence we can write dy by dx at psi is equal to constant right? At psi equal to constant, and what we can write? D psi by dy by dx at psi is equal to constant is equal to v by u. Right? So this is the equation for the streamline that we already know. So let us write the equation for the equipotential line. For equipotential line, phi of x comma y is equal to constant. Right? So along this line, we can write d phi is equal to dou phi by dou x into dx plus dou phi by dou y into dy, that is equal to 0. Right? So this equation can be written as d phi is equal to u dx plus v dy is equal to 0. So if from this equation, if we solve this equation, we can finally get dy by dx is at phi is equal to constant, that is equal to minus u by v. Right? By solving this equation, we can get u. But here we know already dy by dx is equal to, at psi is equal to constant, equal to v by u. Dy by dx at psi is equal to constant. We have the equation v by u. Right? So we can finally write the equation as dy by dx at psi is equal to constant is equal to 1 by minus 1 by dy by dx at phi is equal to constant. So this is the relationship between the stream function and the potential function. Right? So in our today's discussion, we started with the circulation, and I said the circulation is the definition given by Frederick Lancaster, Wilhelm Gutta, Nikolai Dvorsky at a different location of the world, and they have concentrated on one particular thing, which is circulation. So circulation is simply the negative of the line integral of velocity around a closed curve in the flow. Right? And we have discussed about this in the airfoil, and then we want to equate it to the vorticity, and we have discussed about the circulation per unit area. Right? And then we have started with the stream function, and where AB and CD are the two streamlines, and we remember the water flow in the hose in the garden, and we consider a two-dimensional flow here, and by that way the distance between the AB and CD is del n, and we know that the del n is the mass flow in the del n is a combination of mass flow in the del y and minus del x, and then we have written this rho u del n, and then we have the equation finally d psi by d psi, right? And then we have written the rho u is equal to dou psi by dou y, and rho v is equal to minus dou psi by dou x. Is the equation for streamline and Cartesian coordinate system. Then the equation in polar coordinate system, cylindrical coordinate system. Like that we have written. So by considering the incompressible flow, we have finally arrived at u is equal to dou psi by dou y, and v is equal to minus dou psi by dou x. Then we had a discussion on velocity potential. The velocity potential, we started with the consideration of irrotational flow, where the vorticity is equal to del cross v, that is equal to 0 for a rotational flow. And by that way, we have discussed that the gradient, the curl of the gradient of a scalar function is equal to 0, right? And then we have defined the velocity UVWO in terms of the potential function. And we had a discussion on the 3 points between the phi and the psi, right? The difference between the velocity potential and the steam function. And we have defined that a rotational flow described by the velocity potential phi is called potential lines, potential flows, right? Then we started studying about the relationship between psi and phi. We know that the line of constant phi is an isoline, and the line of velocity potential is equipotential line. In the other way, the del phi, if it is tangent at every point, is gradient line. The corresponding line we can say that as a streamline, and the relationship between the two is actually written as dy by dx at psi equal to constant is v by u, and here it is minus u by v, and by that way we finally arrive to the steam function, the relationship between the steam function and velocity potential. Thank you very much. I stop at this point.